Thank you so much. Okay, so there's a lot of technical advances that we're having in science that are really bringing us to the ability to have this sort of uncertainty information in our data. So we have advances in storage, we have more processors, we have higher resolution displays, we have greater bandwidth, and we're also having more advances in simulation. So we have higher resolution grids, we have longer runs, excuse me, we have more sophisticated models and a much better understanding of the parameters that are going into these models, which leads us to lots and lots of complex data. So data uncertainty is becoming much more important in these contexts. So data sets are typically considered incomplete without an idea of the uncertainty within the data. You can often see this when data is presented within scientific papers. Uncertainty is typically, in my field, considered an umbrella term for things like error, accuracy, confidence level, pretty much anything that reduces the reliability of the data. And really, the definition depends on the field or application that you're looking at. So as an uncertainty visualization specialist, we can usually use this term interchangeably in terms of the visualization pieces, but really when you're starting to go to the data domain, it is much more specific in terms of how they quantify the data. So really, uncertainty is fundamental in the science behind the visualization, so why don't we see this more in visualizations themselves? So we know visualization is really communication. So this is a mechanism for understanding large amounts of data. We want to be able to easily convey information using the human perceptual system, which is one of our highest bandwidth systems. Really, we were trying to translate the data that we have into some sort of visual metaphor to expose the relationships and the patterns and the features that we have within that data for understanding. So some of the challenges to uncertainty visualization are the data display is already complicated. We already have high dimensional data sets, and we're having challenges displaying those without information of uncertainty. So adding in uncertainty can do things like add visual clutter. It can complicate the display such that the data is actually obfuscated. And we can actually lead to a less clear understanding of the data that we're actually seeing. So one thing to think about when you're trying to incorporate uncertainty into your visualization is whether or not it's a primary or secondary aspect of the visualization. Is the uncertainty really what you're trying to convey, or are you trying to convey the information held within the data and on top of that give some sort of indication of the reliability? And this is a very fundamental idea of which one is the more important aspect. So which one do you want to use more readily accessible visualization metaphors to show to the viewer so that they can understand one better than the other? So for example, toggling uncertainty displays on and off kind of gives it this feel of a secondary aspect of the data, whereas the main display will show you what the data actually shows, and then the secondary aspect will be the uncertainty that you toggle on and off. Or another thought is about whether or not the uncertainty that you want to show is high uncertainty, where you don't know a lot about the data, or low uncertainty, where you have very high reliability of the data. Another question is, what is the appropriate visual metaphor for uncertainty? In much of the early work that was done in the late 1990s, blurring and really just smearing the data was one very relevant way to do this. But really the problem with blurring is that you can't actually see what the data is underlying it. You can say, hey, this area of the visualization is hard to read, so I assume that the data underneath it is very uncertain, but that's about all you can get from that kind of visualization. So what the abstraction is that you're trying to show with the uncertainty visually is very important to think about. And how do people actually read that abstraction? Are they getting the information out that you really want them to see? Likewise, because there is no singular definition of uncertainty, there's no singular solution in terms of conveying that within your visualization. The location of the uncertainty might be important, or the gross magnitude of the uncertainty might be important. There's also issues with if it's missing data, perhaps you just don't want to show any information there, or perhaps you want to highlight that there is no information there. So it's really a question of what is your specific application and what is the task that you're trying to do with that data. So the general approach to uncertainty visualization starts with the quantification of the uncertainty, typically through statistics. That leads to some kind of reduced data set. Often we use things like some sort of statistical summaries to kind of estimate what the uncertainty is within the data. And then you map that to some kind of visualization variables. So I'm going to start out looking at some of the sources that we have of uncertainty. So experimental uncertainty is one that I think we can all relate to, where you are measuring something multiple times using the same equipment at the same time, and you get slight variations within that measurement. This is also thought of as observational error. And we can kind of see this also in terms of like sensors and things like that. Model uncertainty is the fact that we are computationally estimating these phenomena that we are investigating. And oftentimes, these models do not completely map the entire complexity of the phenomenon. There might be inadequacies. There might actually be biases. There might also be multiple models that you're looking at, and they have excuse me, they don't agree with each other. So this is also known as model bias or model discrepancy. Parameter uncertainty is something that you often see in things like ensemble data sets. So you have a bunch of model parameters, and they can easily affect the results of a model run. And oftentimes, you want to understand the way that these parameters affect the run, and so you get things like ensemble outputs. And these parameters are often multivariable, so you have a high space going into the model, and you often have a high dimensional space coming out. Algorithmic uncertainty relates to the fact that we're doing this computationally. So there's things like quantization, numerical error, the translation of the model to the computational machine. And so we see this no matter what we do because we're doing it computationally. We're doing a discretization of a continuous space. Interpolation is basically the lack of available data and the fact that we're estimating between these two data sets, data points that we have. And this really is related to the type of interpolation that you do. You can think about this also as the fact that we're running everything on these grids, and grids, you can be arbitrarily fine or arbitrarily coarse. And then, of course, you have things like missing data, faulty sensors, bad data. There's a whole host of other sources of uncertainty. So we can kind of think of uncertainty as two different categories. The first one we think of as epistemic, or also known as systematic. And this is things that we could potentially know, but we don't know in practice. So for example, we have insufficient measurements, we have bad modeling, we have missing data. We could potentially resolve those issues with better models, better sensors, better tracking of data. So this can actually be reducible. So hopefully we can, for the most part, relieve the epistemic uncertainty that we have within our systems. Aleatoric or statistical uncertainty is the fact that these runs often produce non-deterministic results, such as throwing dice, and you can't actually eliminate this type of uncertainty through better models or higher computation. So the idea is that we mostly want to be working with statistical uncertainties, which are basically the random fluctuations of measurement. So again, the propagation of uncertainty comes in a lot of different places, specifically when we're talking about visualization, because it can come from the data itself, it can come from some of the derivations and the transformations that we do to the data to get it into the computation and then to eventually get it into the visualization. So there's a lot of different sources of this, and so it's also questionable as to when do you actually want to pull out this uncertainty information. So do we really want to have uncertainty from the collection to the derivation to the visualization, or do we just want to focus on one of those pieces? So back to quantification, the main goal is to reduce the epistemic uncertainties to aleatoric. So we want to basically try to reduce the unknowns that we can mitigate to statistical uncertainty as much as possible. So common statistical representations of uncertainty. Typically, we think of most of our data as coming to us in the form of probability distribution functions. So these can be continuous or discrete, and this is basically a independent random variable that appears in some sort of distribution form. This is like the frequency of the outcome. You can also have this categorically. So you have discrete random variables with a finite set of outcomes. And so basically you start to look at statistics that you can do within these PDFs. So mean is a common one where you basically average everything and get the most, the average value across everything. Median is the middlemost value, so that's an actual data point within the probability distribution function. So the difference between the mean and the median is that the mean is actually calculated, so it might not actually occur within the, as a realization of the model. And standard deviation is the spread of those values within the PDF. So this is typically what we think of as uncertainty. This is the most commonly used statistic to convey uncertainty. Mode is the most commonly occurring value, and this one is a little challenging in that usually you think of a normal distribution or the bell curve where you have one mode that is right in the middle, but oftentimes in real data you get multimodal distributions, and a lot of the statistics that we use don't actually account for that. And then finally, one that I like to talk about just because it actually occurs in a lot of the evaluations of PDF statistics is the support or range. So what is the actual numerical range of the PDF that you're looking at? So you can actually have PDFs that look exactly the same if you're comparing them, but the ranges might be completely different. And that can actually affect the way that you interpret the statistics on those PDFs. So now I'm going to go over a little bit of ways that we've been looking at these kind of PDFs for a very long time. So box plots are one of the earlier ways that we look at this stuff. And so this is looking at a one variable probability distribution function. And you basically have this box that has the 50% of the data within the box with the median highlighted with a line. And then you have things like the minimum and maximum values and possibly some outliers highlighted with some kind of indication. There's been a lot of work in trying to kind of mess with the box plot. So here's three different representations of visual modifications. So I just like the first one because it was Mary Spear, and she did this in 1952. So there's ladies been working on this for a very long time. And then Tukey sort of popularized it in 1977 with the quintessential box plot. And then further on there is the Tufte minimalistic box plot that basically removes the box with the idea that the box is kind of giving you this false sense that everything is actually within this rectangle of data when that's not necessarily true. So his idea is reduce the ink to paper ratio and just kind of somehow indicate where the percentiles lie. There's also been additions of the density information to try to also kind of get out of this box idea. So here's 4 different ones that kind of start with, okay, well, we're just going to show you what the density is at each of the quartiles and kind of draw these diagonal lines or maybe give you some kind of density plot, eventually getting up to the violin plot, which I think we've all sort of seen. So this is just basically a symmetric representation of the full histogram of the data. In addition, people have tried to add things like sample size and confidence levels through modifying the thickness of the blocks or somehow giving indications through dashed lines or notches. And finally, trying to express more higher dimensional statistics such as mode and moments through thicknesses within the lines. So this, again, was all done sort of fairly early in terms of understanding the box plots. But one of the problems with the box plots is that we are assuming sort of this Gaussian distribution, even if this kind of stuff is trying to sort of express that maybe this isn't quite Gaussian. We still sort of interpret this as Gaussian anyway. So what else can we do if we don't have Gaussian, or how can we express things that may not be Gaussian? So this is the summary plot that I did in 2010. Basically, the idea is instead of having a single plot showing just the median and standard deviations, really is to sort of get a lot of information and somehow map it on top of each other so that you can get some sort of signature of a probability distribution. So here's sort of what the idea is, to really highlight variance from normal. So highlight locations probability distribution functions that are not what you would normally expect on a Gaussian distribution. So just to give you an idea of what the box plot shows, we start with an abbreviated box plot that shows what we've been talking about so far. We add a moment plot that has the mean, the standard deviation, the skew, as in like where is the big area of the probability, the distribution at, where's the frequency at, and also things like kurtosis, which is the peakiness of the distribution, and tail, which is where is the long end of the small occurring values. So then we're also adding a histogram that is color-coded, and also we did a little bit of distribution fitting depending on the application. So we had some canonical distributions that we would give you in this dotted line to sort of help you understand, is this a Gaussian distribution and how close to it is it? So again, back to here, the idea of this particular visualization is to just choose some clusters of the data that's on the map, and these points that are on the map are sort of representational locations, probability distribution functions for those areas. And then we showed this in this line plot. And so as you can see, these are a little complicated and visually cluttered. So I've pulled them out so you can see just the abbreviated box plot in the line graph, and then you can see the summary plots pulled out. And this kind of highlights the problem with this kind of approach is, first of all, we're estimating this 2D data set with a few summary plots, and that these glyphs are very complicated, and so you really have to use them very cautiously. But again, this is mostly looking at data in terms of pulling out one-dimensional aspects of the data, and really we're looking at much higher dimensional data where glyph-based approaches are really not going to work. So again, a lot of my work in my grad days was looking at ensembles, which are multi-run simulations that are looking at a space of input parameters, attempting to mitigate things like model error and unknowns in initial conditions, and really come out with multiple models that express the range of outcome options. So really we have a collection of data sets that we have full realizations of a run, and these are run multiple times, and so you can actually look through each member of your ensemble and see a full realization of a model run. So ensembles are very complicated because they're multidimensional in space and in time. They are multivariate, so you're simulating many, many variables over many parameter spaces. And they're multi-valued, so for every grid point, you have multiple variables with multiple values. And so you can get very large ensembles, gigabytes of data. This is very hard to manage. So the statistics that you run on these models is really about combining the different models together to understand the effects of the parameters and get some kind of idea of what the output space looks like to be able to kind of understand the most probable outcomes. So to look at this kind of stuff, I took the Ben Schneiderman's information-seeking mantra, which is overview, zoom filter, and then details on demand. And so really I looked at overview, summary, and details. And when I first sort of started thinking about this got me a little confused about what is the difference between these things. So an overview versus a summary. So an overview is actually showing all the data at once. And so back in the good old days, they would actually print out a bunch of different plots and lay them out at a table so you could actually see all of the data at once. And so this is sort of this this matrix of 2D plots is kind of that idea. Like, here's all the data, and in this particular image, you can see that, okay, it's a lot of data. It's hard to kind of compare everything and see what's going on. But you can imagine this for much bigger data would be even harder to understand. So this is relying on things like manual search, and it's relying on the fact that you would be able to see all of your data at once. And so we have problems like finite screen resolution, or the size of your table is going to be finite, so you can't actually see all of the data. So overview is becoming very, very challenging in the kind of data that we're seeing today. So the summarization is coming in and trying to aggregate things to give us a general idea of what is in your data. So for the ensembles, because you have so many dimensions in terms of space and time, you kind of have to choose where you want to aggregate over. And so oftentimes we do things like automate these summaries, so you can kind of go through and have the computer automatically choose a bunch of different dimensions to aggregate over, and then you can be presented with possibly something like an overview of summaries. And this gives you kind of an idea of the types of questions that you would want to start to explore and understand within your data. So I like the idea of aggregation, specifically because it mimics the human visual system. We do this every day, all of the time. So as you know, we have like this blank hole in the middle of our viewpoint, which is actually related to where the nerves go from our eyes into our brain, but we fill it in automatically. Our brain does this. We also know of things like change blindness. So we sort of the brain kind of fills in what we think we know, even if it's not what we know. In addition, the computer, our finite screen resolution, we kind of fill in the fact that this is a discrete representation of what we see as a continuous image. So we kind of do this implicitly. So the idea of aggregation is, to me, kind of similar to what we do already in the human visual system. So how do we actually reduce data using these summaries? So when you start with a project, how do you know what dimension you should summarize over? Do we know that mean and standard deviation is actually appropriate? Are we actually looking at multimodal distributions where that actually doesn't give us reliable information? And do we actually need multiple summarizations to look at this data? So the software that I developed in grad school to look at this stuff is called Ensemble Viz. And it's actually a user-driven, component-based framework to kind of, instead of answering those questions specifically, to give the user multiple ways to look at the data so that they can answer it themselves. So looking at multiple summaries, being able to explore the range of the forecast opportunities, revealing the probabilities of the outcome, and really interrogating the ensemble. So the first thing that we looked at were global summaries. Oh, and my movie is working. That's amazing. So this would be aggregating over the grid points. So if you can think of sort of the ensemble as like a sandwich of maps over the North America, sort of smushing those all down, and at each grid point, basically finding the mean and standard deviation and showing that via color mapping and isocontours. And so this is, again, at a single time step, and just sort of smushing everything down into a general idea of what does it look like and where do we know that there's high variation. On the bottom, there are these time summaries that's actually more like a film strip view that does that compressed visualization but across time. And so you can actually scroll through and start to see where things start to change. And if you find something interesting, you can double click and it will be shown in the main map. The contour summaries are starting to follow isocontours, so changes of specific values across the map. So this allows us to see things like divergence and variation. So here, the user is looking at a plume chart of some value. I don't recall what it is. Oh, HCT 5000. Yeah, I don't remember the data that well. But you can start to see the spaghetti plot and how the different models, they're each colored with a different color, and you can see them start to diverge. And you can kind of mess with the contour value and see where the models no longer agree with themselves. The other way to start looking at this stuff is through spatial summarization. And so this is actually selecting areas of interest and then showing the individual model results for those areas. So you can think of selecting a single grid point and seeing how each of the models for a particular variable at that particular grid point change across time. So on the top is sort of our idea of a box plot of the data on the bottom. So kind of looking at the minimum and the maximum models and some kind of aggregation within that gray band. And so on the bottom is actually, you can see all of the model runs that are individually colored. And the legend actually allows you to turn the models on and off, and it will recalculate the median value, which is the black line in the center. And we did this because we were talking to some of our scientists, and they had particular models that they did not particularly trust. And so they liked to be able to turn those models on and off so that they could actually get a visualization that they believed in. This might be the last. The last summary type that we did was query summaries. And this was actually looking at SQL type summaries to find things like heat stroke. So where in the country at a certain time is it hot and also humid? And so this is an SQL type query that we then would retrieve and use color and isocontours to show areas of high potential heat stroke. And we could have done other types of queries like this. So another aspect of this is that you're looking at different audience types when you're trying to show this. So the previous work that I was talking about, we were specifically looking at people that were trying to understand the ensembles and predict things like heat stroke or probabilities of weather occurrences. But oftentimes these visualizations are used by multiple audiences. So is there a way to be able to potentially show visualizations from a single workflow to different audiences? What are the differences in usages? And is there anything that we're actually doing correctly? And so to do this, this was work that I did with Sandia National Lab. And we were looking at material models, which are basically equations of state. And they have basically different realizations of different material surfaces. And so what we actually ended up doing is there was a small collection, I think 4 or 5 visualization people that got the same data, and using the tools that we had, we all made different visualizations of the uncertainty of these surfaces. So this was what I did, where it was basically, all right, let's just show a bunch of the surfaces. The color map is just the temperature or some kind of variable of the surface. But really the thing to look at is the fact that there's different realizations of a single surface. And it was not really to give the people the best visualization. It was just trying to spark discussions and have different visualizations to try to figure out what is the best path forward. And again, I did a simple prototype where it was basically the min and max of the surfaces along with the mean. And so what we actually did was we ran a user group, and so we all came together and showed off all these different realizations of these visualizations. And one of the most interesting things that came out of it is that on the bottom here, I'm using the mean and standard deviation, which is not valid realizations of this material model. So as I show here, these point-wise statistics of this model space are not valid realizations, and these modelers are not having it. They do not want to see this. It's not helpful for them at all. So this comes back to how do we actually do statistics on these higher dimensional spaces. So coming back to this kind of idea of line charts, I started working with Mark Getton on functional box plots. And so this is his work on functional box plots, where the idea is trying to find box plot-like statistics on 2D functions. So you have this space of a bunch of 2D lines, 2D curves rather, and you could potentially do box plots at, say, these specific discrete points along the general location of the lines, but that doesn't actually give you a real idea of what is the middlemost function. So he looked at something called band depth, which actually interrogates each of the functions within your collection and finds the one that spends the most time within the center of the function set. So basically, he discretely goes through each of the locations and finds the value for each of the functions and determines which one at each location is the center, and then looks globally at which one spent the most time within the center of that set. And then he can use that to basically do counting statistics, giving you an ordering to give you box plot type statistics. And so we took that initial approach and moved to surfaces. And so here we actually were able to do some box plots on a collection of images, so that you can find things like the middlemost image, a percentile type statistics on these different images. So this is literally just taking the 2D surface and extending to 3D via, it's more like 2.5D, but via the color of the image. And so this gave us kind of this idea of how to classify surfaces in this way. And so we've actually seen some of this box plot stuff being used in things like contour box plots, some hurricane tracking. And so I like this approach a lot. And there's been a lot of great stuff that has been done by some people in Florida and some people in Utah. Okay, so going back to probability distribution functions. Again, one of the problems is how do you look at these probability distribution functions that are actually 2D surfaces that each point has this PDF, but it's really hard, like with the glyph stuff, you can't really like evaluate each of these PDFs at each of these grids without really going through and like one by one looking at things. And so the idea in this work is to somehow be able to compare the probability distribution functions at each grid point simultaneously and in a way that you can actually publish. So how do we actually do this in a way that doesn't rely on lots of interaction, lots of interrogation by the user? So the idea is, well, actually, I'll look at the data. So the data that we have is this electrical conductivity of the heart. So basically, the data is a 2D grid across the torso, and the goal is to simulate how signals from the heart propagate across the torso. So the idea is that a patient, for example, would have the EKG meters on their body, and that's trying to detect like if there's some kind of heart issue, like are they having a heart attack while they're laying in bed? But oftentimes, simply the roll of a patient would light off these monitors, and the nurses would come running in thinking there was an event happening, and really they just rolled over. And so the idea is to sort of simulate what the different potentials are across the body to try to understand kind of the range of acceptable variation in the EKGs. So the problem is that all of our tissues have different potentials of conveying electrical conductivity. So specifically, the simulation looked at fat, lungs, torso, cavity, and muscle. And so the heart is the white spot in the middle, and then the simulation looked at the different tissue types across the chest, in just a single slice across the chest. So the study looked at the impact of the variation on input conductivity. So what are the different conductivities of these different tissue types? And you can imagine that singularity, each of these different tissue types have different conductivities, but probably they have individually different conductivities within the same tissue type. So this is just a Monte Carlo simulation. So we basically varied the type of the values of lung conductivity, plus or minus 50% from the initial reference value, and then ran 10,000 realizations of the potentials across the entire torso. And so you can see we've got a pretty refined grid that we were simulating across. So we got lots and lots of data. And so the paper on this simulation itself used these two images to convey the mean and the standard deviation across the torso. And so you kind of get this idea of, well, here's what the mean values are. So obviously, the mean of conductivities is one direction on one side of the torso and another direction on the other side of the torso. And the standard deviation, okay, so where that's very low mean, you have very high standard deviation, and it looks like you can kind of make some ideas of justifications of these particular statistics, but they're not very clear. I don't really understand. I couldn't necessarily say, okay, right there where the lung is, here's what the mean value is, and here's the standard deviation, and here's how I trust it. So the idea was, how do we more specifically show what's happening in this model? Again, is mean and standard deviation even appropriate for this kind of exploration? And how do we look at this without looking at every single grid point individually? So we started to try to think about, what do the PDFs look like across the domain? Is there a way to kind of categorize the change in probability distribution from grid point to grid point? Can we compare these somehow? So the idea is to actually compare each one of the PDFs at each grid point to a singular canonical distribution and get a color map of that, that difference. So looking at things like, say, this canonical Gaussian distribution, what does each of these distributions, grid point distributions, look like in comparison? So that's the color map. So we defined here basically 2 different distributions, and we ran, those are the stripes that you see. And so you can see that one is very similar to the Gaussian and one is very much not. And specifically, we're looking at 3 different distributions, so a uniform, a Gaussian, and a beta, but you could obviously add these, add more to these distributions, but we allowed the user to change the different distributions that we were looking at. But the problem also became that the range, like I mentioned earlier, it changes between each of the, let me go back to this image. The range actually changes across the torso of values within the probability distribution functions. So we started out just doing a color mapping comparing to a singular Gaussian distribution, and it looked great, but then it turned out that on one side, so you can see sort of this dark greenish area, on that side, the range of the distributions was much different than on the opposite side of the torso. And so we were not actually getting a very clear picture of what the distributions actually look like in comparison. So we had to add then a bivariate color map, which is what you see here, where the darkness actually shows the width of the range, so that you can then understand that, okay, they're similar color, which means they probably look similarly in terms of the shape of the probability distribution function. However, the range is much different, which means the size and the values of the probability distribution are much different. And so we believe that this is a much more accurate visualization of the data that came out of, and this is just the mean, the data that came out of this model. And this would be probably a better way to show the results versus this. And you could certainly map like standard deviation also in terms of how to look at this stuff. And so that was kind of our idea of how to actually start to do some comparison work. So I think possibly the comparison of these distributions is probably a good way to start looking and thinking about this kind of data in the future. And so the next work that I did was looking at some categorical data. So specifically, I was looking at the brain web, which is actually a collection of volumes of the brain, 8 different volumes that are that basically show the probability of a particular tissue type. So you can think of a single volume that has a brain in it, and it's the probability of each of those voxels within that volume to be, say, the skull. And so we have all these different tissue types, and so we have a volume for each of those tissue types, and all of the voxels, they all add up to 1 if you add all the voxels together. And so here's just a slice through that data, color mapped for each of the tissue types. And so you can see that, okay, in the middle, you've got gray and white, et cetera. But so to be able to look at this data, you can do a single slice through the 8 volumes, or you could potentially look at each of the volumes themselves. But this is kind of a big data set, hard to look at. So our idea was to look at information theory, specifically at entropy, which kind of shows the amount of randomness in a variable. So, excuse me. So if you have an absolute, you know absolutely that one particular voxel is a tissue. So say in the corners, you know its background, then there's no entropy. But if there's a voxel that has lots of different tissue types, then you have high entropy, and then you know that categorizing that particular voxel as a particular tissue is problematic. So here's a visualization of that same slice, but with entropy color mapped from high to low. So you can definitely see that around areas of the skull, it's harder to classify those particular tissue types. So again, the higher the entropy is, the more white that you have in this color map, and the higher the uncertainty in those areas. So our idea was to then combine the original color map with the tissue type with the uncertainty, or say entropy color map. And so here's actually a visualization of that, where you reduce down to 4 tissue types because it does become hard to sort of see all of these different tissue types at once. And then moving this into 3D, we were looking mainly at a single tissue type. So the black and white is just the entropy of the data within that volume. And then here's actually some brain matter with the white specks, or where the uncertainty or the classification of that tissue type into this brain matter is uncertain. So really, uncertainty is not a singular definition. Like, as you can see, there's a bunch of different examples of where there's uncertainty in different aspects and areas, and trying to address the visualization of uncertainty and even the quantification of uncertainty in each of these domains is not a end-all be-all. So it really depends on the questions of the application and the tasks that you're trying to do. And so the main focus of the work that I'm continuing is there other types of summary techniques that we should be looking at? Are these summarization techniques that we're using so far actually good or valid? And how do we actually know that the uncertainty that we're looking at is being conveyed to the viewer in an appropriate way? So again, I want to continue to increase the vocabulary within the visualization community of uncertainty measures. The visual metaphors for uncertainty are still being developed. And again, it's going to be hard to get away from interaction, particularly with these very large data sets. So thank you so much. If anyone has any questions, I'd love to take them. And you guys are always welcome to send me an email. Come visit at NREL.